There's a stretch of ground in northern Wyoming that people have walked over, driven across, and dug into for more than 130 years without ever knowing what was actually underneath their boots. Ranchers grazed cattle on it. Coal crews blasted through it. Drill rigs punched hundreds of holes into it looking for exactly one thing, and that one thing was coal, the fuel that built this part of the state. Nobody was looking for anything else, because nobody had a reason to. The rock didn't glow. It didn't spark a Geiger counter. It looked, to every eye that had ever studied it, like ordinary claystone, sitting above and below an ordinary coal seam. The kind of rock a mining engineer glances at once, logs in a notebook, and then never thinks about again. Picture the routine that had repeated itself at that mine for generations. A drill bit grinds down through soil, then through a pale band of clay, then into the black coal seam everyone actually cares about. The core comes up in long, cylindrical sections laid out in wooden trays and labeled by depth. And a geologist walks the row, checking each segment for the properties that determine whether the coal underneath is worth mining. How much heat it releases when burned, how much ash it leaves behind, how much sulfur and moisture it carries. The pale clay above and below gets a glance, sometimes a note, and then it gets moved out of the way. That's what overburden means in the mining world. It isn't nothing, but it isn't the point either. And after 130 years of that exact routine, nobody at that mine, or at any coal mine like it anywhere in the country, had a reason to ask what else might be sitting inside the rock they were discarding by the truckload. In the spring of 2023, somebody finally asked. And what came back from the lab didn't make sense at first. Buried inside that plain gray clay, in a defunct mine north of the small city of Sheridan, sat some of the richest concentrations of medium and heavy rare earth elements that scientists at a United States national laboratory had ever measured outside of Western China. Not a trace. Not a curiosity. A deposit large enough that, within 2 years, people in Washington were calling it one of the most strategically important mineral discoveries on American soil in living memory. And a company that had spent its entire history digging coal suddenly found itself standing at the center of a fight over who gets to build the next generation of fighter jets, electric cars, and wind turbines. This is the story of how that happened. Why a handful of misfit atoms buried in Wyoming clay can decide who wins that fight, and what's already changing because of it right now, months and years before anyone knows for certain how the story ends. To understand why anyone would care this much about a cylinder of rock pulled out of the ground, you first have to understand what rare earth elements actually are, because the name itself is a little bit of a lie. There are 17 of them. 15 belong to a chemical family called the lanthanides. Sitting in that odd detached row, usually printed at the bottom of a periodic table, the row that gets pulled out and floated below all the others, because if you tried to squeeze it into its proper place, the chart would need to be nearly twice as wide. Add 2 chemical cousins, scandium and yttrium, that behave enough like the lanthanides to travel with the same crowd, and you've the full set of 17. Names like neodymium, praseodymium, dysprosium, terbium, europium, and cerium don't come up in casual conversation, but they aren't actually rare in the way gold or platinum are rare. Cerium, the most abundant of the group, is more common in the Earth's crust than copper. Even the scarcer members of the family, like thulium and lutetium, are more common than silver. What makes the lanthanides so unusual is happening down at the level of the atom itself. Every one of them fills an inner electron shell, tucked underneath the outer electrons that normally govern how an element behaves chemically, the kind of arrangement that gives them nearly identical chemical behavior while still leaving each one with its own distinct magnetic and optical fingerprint, depending on exactly how many of those inner electrons it carries. That combination, Nearly identical chemistry paired with wildly different physical properties is what makes the whole family so valuable. And it's also exactly what makes them such a nightmare to pull apart from one another. What's actually rare is finding them concentrated enough, in a form clean enough, to be worth digging up. Rare earth atoms almost never gather themselves into a nice, tidy, high-grade seam the way a gold vein does. They scatter. They hide in trace amounts inside dozens of other minerals, chemically similar enough to each other that separating one from the next is a brutal, multi-step industrial process. A typical operation starts by crushing and roasting the ore to break down its mineral structure, then dissolving it in acid to pull the rare earth atoms into solution. From there comes the truly punishing part, solvent extraction, a process where the dissolved rare earths are repeatedly shaken between two liquids that don't mix, an acidic water layer and an organic solvent layer, so that each element migrates toward one side or the other by a fraction of a percentage point more than its neighbors. Imagine trying to sort 17 nearly identical marbles by weight, when the heaviest and the lightest differ by less than the thickness of a coat of paint, and you are only allowed to sort them a tiny fraction more accurately with each pass. That's roughly the scale of the challenge. Because neodymium and praseodymium, or dysprosium and holmium, behave almost identically in that shake, getting a clean separation between them can require running the mixture through hundreds of these extraction stages in sequence, sometimes housed inside buildings that stretch the length of several football fields, before the output finally comes out pure enough to be useful. Only after that does the final rare earth solution get precipitated out as a solid and baked in a furnace, or calcined, into the stable oxide powder that actually gets sold and shipped. A mining company can spend a fortune drilling into rock that technically contains rare earths and still walk away with nothing, because the concentration is too thin, the mineral form is too stubborn for that acid and solvent chain to handle economically. Or the deposit is tangled up with radioactive thorium and uranium that make processing a regulatory and environmental nightmare all on its own. So the word rare doesn't describe how much of the element exists on the planet. It describes how rarely nature hands it to us in a form we can actually use, and how expensive, chemically brutal, and technically demanding it's to finish the job once we find it. And we use an enormous amount of what comes out the other end of that process, mostly without realizing it. Grind a few rare earth atoms into the right alloy, and you get the strongest permanent magnets ever manufactured. Magnets that don't lose their pull even when they get hot, which matters enormously once you put them inside something that generates heat by design. The reason those magnets are so strong actually comes down to something you can picture without a chemistry degree. Inside any magnetic material, there are microscopic regions called magnetic domains, tiny pockets where atoms line their magnetic fields up in the same direction. In an ordinary piece of iron, those domains point every which way and mostly cancel each other out, which is why a nail isn't a magnet on its own. What a rare earth atom brings to the party is an unusually large, unusually stubborn magnetic field at the level of a single atom, produced by electrons sitting in that same inner shell that makes the elements chemically similar in the first place. Alloy those atoms with iron and boron in the right ratio, then expose the mixture to an intense external magnetic field while it solidifies, and you force nearly all of its internal domains to lock into the same direction and stay there, the way you might comb 1,000 tiny compass needles until every single one points the same way, and then freeze them in place. The result resists losing that alignment even when you drop it, heat it, or try to demagnetize it with an opposing field, a property engineers call coercivity. And it's that stubbornness, not just raw magnetic strength, that makes a rare earth magnet dramatically more useful inside a motor than an ordinary magnet twice its size. Neodymium and praseodymium form the backbone of that magnet, the two elements responsible for most of its raw magnetic strength, and together they sit inside the drive motor of nearly every electric vehicle currently on the road. But a neodymium magnet on its own starts losing its grip as it heats up, and an electric motor spinning at high speed for hours gets hot fast, eventually crossing a threshold called the Curie temperature, past which its magnetic alignment collapses entirely. That's where dysprosium and terbium earn their keep. Added in small percentages specifically to raise that threshold and keep the magnet structure stable at high temperature. Which is exactly why those two elements, present in far smaller quantities than neodymium, often carry a far higher price tag and a far tighter supply. Swap the base metal from neodymium to samarium and cobalt instead, and you get a different magnet entirely, one that holds up under even more extreme heat and resists demagnetizing under mechanical stress, which is why samarium-cobalt magnets, despite being weaker overall, are the preferred choice inside missile guidance systems and other military hardware that's to keep working after the environment around it turns violent. The rest of the family earns its keep in quieter, less obviously dramatic ways, and most of them are probably sitting within arm's reach of you right now. Cerium and lanthanum are the workhorses of oil refining, used as catalysts that help break heavy crude down into gasoline, and cerium doubles as the compound that polishes glass, including the windshield in front of you and the mirror behind you. Europium and terbium once lit up the screen of every television and computer monitor built before flat panels took over, glowing red and green under an electron beam. And terbium still shows up today in certain energy-efficient lighting. Gadolinium gets injected directly into patients before an MRI scan because its magnetic properties make the resulting images sharper and easier for a radiologist to read. Scandium, despite being chemically distinct from the lanthanides, hardens aluminum alloys used in aerospace manufacturing without adding meaningful weight, and is increasingly used in a newer generation of solid oxide fuel cells. Yttrium shows up in LED phosphors, in certain high-temperature ceramics, and in specialized superconducting materials. And erbium, an element almost nobody outside a materials science lab has ever heard of, sits inside the fiber optic amplifiers strung along the undersea cables that carry the vast majority of the planet's internet traffic, boosting a fading light signal back to strength every so many miles, so a video call from Wyoming can reach someone on the other side of the world without breaking apart. Set aside the exotic applications for a moment and just look around an ordinary room. The tiny motor that makes your phone buzz, the driver inside your wireless earbuds, the actuator that reads and writes data on a spinning hard drive, the brushless motor inside a cordless power drill or a robotic vacuum, the pitch motor that angles a wind turbine's blades into the wind. All of them lean on some version of the same neodymium-based magnet. This isn't a family of elements waiting quietly in a laboratory for the future to arrive. It's already arrived, and it's already load-bearing. None of that's exotic anymore. It's infrastructure. A modern economy, and especially a modern military, runs on rare earth magnets the same way an older economy ran on steel. And that dependence is precisely why a claystone layer in a Wyoming coal mine turned into national news. Because here's the part that should stop you. Almost none of the world's usable rare earth supply comes from the United States. And it wasn't always this way. For decades, American mines, particularly one enormous open pit sitting out in the Mojave Desert of California called Mountain Pass, supplied most of the planet's rare earths. The story of how that dominance slipped away and what it eventually took to start clawing even a piece of it back tells you almost everything you need to know about why Wyoming matters now. Mountain Pass was discovered essentially by accident back in 1949, by prospectors who were actually out searching for uranium and instead found unusually radioactive rock that turned out to be rich in a rare earth mineral called bastnasite. A mining company began production there in 1952, and through the 1960s, 70s, and 80s, Mountain Pass became the dominant rare earth supplier on Earth, feeding the booming demand for color television tubes, which needed exactly the kind of europium and terbium phosphors this mine produced in bulk. Then two things happened at roughly the same time. China began investing heavily in its own rare earth industry, backed by state subsidies and labor and environmental costs that undercut American production at every step, and Mountain Pass suffered a series of wastewater pipeline spills through the 1990s involving radioactive material, drawing regulatory scrutiny that slowed the mine down at the exact moment it needed to be racing to stay competitive. Production limped along and eventually stopped almost entirely. A company called Molycorp bought the property back in 2008, poured roughly $1.5 billion into modernizing it, and reopened it in 2010, betting that the world's growing appetite for clean energy and electronics would finally reward American production again. It didn't work, at least not on that timeline. China, already sitting on the overwhelming majority of global refining capacity, could simply lower prices whenever a competitor threatened to gain ground, absorbing losses that a smaller American company couldn't survive. That wasn't the first time the pattern had played out either. In the years following the 2010 crisis with Japan, which you'll hear the full story of in a moment, rare earth prices spiked to extraordinary levels, in some cases rising by a factor of 10 within a matter of months, which briefly convinced investors around the world that dozens of new rare earth mining projects, from Wyoming to Canada to Africa, were about to become wildly profitable. Then, almost as quickly, Chinese producers ramped supply back up, in part by formalizing and expanding production that had previously been running through smaller, less regulated operations, and prices collapsed, falling by well over 90% from their peak within about 2 years, a swing dramatic enough on its own to bankrupt a whole wave of the very Western mining projects that the original price spike had inspired. Mountain Pass, saddled with debt from its billion-dollar modernization and unable to survive that same price collapse, followed the same path. By 2015, buried under debt and unable to compete with Chinese pricing, Molycorp filed for bankruptcy, and Mountain Pass went dark again. 2 years later, in 2017, a new ownership group called MP Materials bought the entire property, mine, processing infrastructure, and all for roughly $20 million, a fraction of what Molycorp had spent building it. Notice that gap for a second, over $1 billion invested, and the whole operation sold off for about $20 million, once the market decided American rare earth production couldn't survive a Chinese price war. That isn't a story about geology failing. The rock at Mountain Pass never stopped being rich in rare earths. It's a story about what happens when one country controls the refining bottleneck badly enough that it can simply price a rival mine out of existence whenever it chooses to. And it's the exact risk that anyone betting on Wyoming's clay has to take seriously, rather than wave away. MP Materials restarted mining in late 2017 and has spent the years since trying to rebuild an American supply chain that had essentially been dismantled. And even that rebuilding effort has come with an uncomfortable irony baked into it. A Chinese company called Shengyi Resources holds a minority equity stake in MP Materials and, for years, was the primary buyer of the raw concentrate coming out of Mountain Pass, meaning America's flagship rare earth mine was, for a meaningful stretch of its modern life, still financially entangled with the very supply chain it was theoretically supposed to be an alternative to. That's been changing, deliberately and quickly. MP Materials has been building out its own separation and refining capability at Mountain Pass, so it no longer has to ship raw material to China to get it turned into anything useful. And in 2021, It broke ground on something the United States had not had in decades: an actual rare earth magnet factory in Fort Worth, Texas, built specifically to turn Mountain Pass oxide into finished neodymium iron boron magnets, rather than exporting the raw material and buying the finished product back. That factory has to solve its own version of the separation problem's cousin: taking pure oxide, reducing it to metal, alloying it precisely, pressing the alloy into shape, sintering it under intense heat inside a magnetic field so its internal domains lock into alignment the way described earlier, and then coating the finished magnet against corrosion, since the alloy rusts easily on its own. General Motors signed on early as an anchor customer, planning to use magnets from that Texas facility inside the electric drive motors for more than a dozen vehicle models built on its Ultium platform. The facility's first phase gives it the capacity to produce around 1,000 tons of finished magnets a year, enough to supply roughly 500,000 electric vehicle motors. And MP Materials has since committed to an even larger expansion nearby, a campus expected to cost over $1 billion and eventually employ as many as 1,500 people. There's one more chemical step tucked inside the phrase, mine to magnet, that deserves its own moment, because it's easy to assume that oxide and metal are close enough to the same thing, and they aren't. A rare earth oxide is a stable, relatively easy-to-handle powder, essentially the metal bonded tightly to oxygen, the same reason iron ore looks nothing like a steel beam. Turning that oxide into pure metal generally requires a process called molten salt electrolysis, closely related to the method used to smelt aluminum, in which the oxide is dissolved into a bath of molten fluoride salts, heated to several hundred degrees, and then subjected to a strong electrical current, which pulls the rare earth atoms away from the oxygen and deposits pure metal at one electrode. That metal then still has to be alloyed with iron and boron, cast, ground into fine powder, pressed into shape inside a magnetic field, sintered under heat to fuse the powder into a solid piece, and coated against corrosion, the full sequence described earlier when the Texas magnet plant came up. Every one of those stages, oxide to metal, metal to alloy, alloy to finished magnet, is its own specialized industrial capability, requiring its own equipment, expertise, and safety systems. And the United States is still in the early stages of rebuilding meaningful capacity at nearly every step of that chain. A ton of rare earth oxide leaving Wyoming isn't by itself a magnet. It's the first of several ingredients in a recipe the country is still relearning how to cook from scratch. That last detail matters more than it might seem to at first, because it exposes a bottleneck that a story about mining alone can make you forget. Digging rare earth ore out of the ground is only the first step. Refining that ore into pure oxide is the second, brutally difficult step. But turning finished oxide into an actual sintered magnet, as just described, is a third, entirely separate industrial skill that the United States had also allowed to atrophy almost completely. A country can solve the mining problem and still not solve the magnet problem, which is exactly why the effort at Mountain Pass has had to rebuild the entire chain, mine to oxide, to metal to magnet, essentially from scratch. And it's exactly the kind of downstream capability that any rare earth project coming out of Wyoming will eventually need access to as well, whether that means shipping oxide to a facility like the one in Texas or building comparable capacity somewhere closer to home. America hasn't been trying to solve this alone either. Australia has spent the last decade building the other major alternative to Chinese refining, centered on a mining company called Lynas, which digs rare earth ore out of a deposit called Mount Weld in the remote outback of Western Australia and ships the concentrate roughly 4,000 miles north to a large processing plant it built in Malaysia, chosen originally for its lower construction costs and access to shipping, Though the plant faced years of local protest over how it stores the mildly radioactive waste that separation chemistry inevitably produces, Lynas has become, by most measures, the only company outside China separating and selling a full suite of both light and heavy rare earths at meaningful commercial scale. And it's been racing to add dysprosium and terbium, the two heat-resistant magnet elements, to that lineup specifically because Western governments have been pushing hard for any source of those two elements that doesn't run through Beijing. Between Lynas in Australia and Malaysia, MP Materials in California and Texas, and now Ramaco in Wyoming, a genuine, if still fragile, alternative supply chain has started taking shape outside China for the first time in a generation, spread across 3 different companies, 3 different countries, and 3 fundamentally different kinds of deposit. Wyoming isn't trying to replace that effort. It's trying to become one more leg holding it up, at a moment when the entire structure still rests on a handful of projects that could each, individually, be knocked over by the kind of price war that killed Molycorp the first time around. None of this is unfolding as a purely American story either, even if the mine itself sits entirely inside Wyoming. Washington has spent the last few years leaning on allies to build a wider, more redundant rare earth network, rather than trying to solve the entire problem domestically, an approach sometimes described as friendshoring, sourcing critical supply chains through trusted partners rather than adversarial ones, even when that supply doesn't originate on American soil. Australia, Japan, and India have coordinated with the United States on critical minerals cooperation through a loose diplomatic grouping known as the Quad, aimed partly at pooling investment and coordinating stockpiles across allied countries rather than each nation racing to build a complete, self-sufficient supply chain alone. Washington has also pursued narrower bilateral arrangements, including a critical minerals cooperation agreement reached with Ukraine in the middle of this decade, tied partly to that country's own underexplored mineral reserves and partly to the broader strategic relationship between the two governments. Set against that wider map, Wyoming's contribution looks less like a solitary American breakthrough and more like one domestic node being added to a much larger lattice of mines, processing plants, and diplomatic agreements that Western governments have been assembling mine by mine and treaty by treaty, specifically because no single country, allied or otherwise, currently has enough scale on its own to fully replace what China controls. The United States found out exactly how dangerous rare earth dependence could be back in 2010, in a very specific, very public moment. A Chinese fishing trawler collided with Japanese Coast Guard vessels near a small group of disputed, uninhabited islands in the East China Sea, known as the Senkaku Islands in Japan and the Diaoyu Islands in China, and Japan detained the trawler's captain under its own laws. In apparent retaliation, China quietly halted rare earth exports to Japan for roughly 2 months, without ever formally announcing an embargo. Shipments simply stopped clearing customs. Japanese electronics and auto manufacturers, who depended almost entirely on Chinese material to build everything from hybrid car motors to camera lenses, watched prices spike with no warning and scrambled for alternative supply that, at the time, barely existed anywhere else on Earth. The message landed everywhere that paid attention. A country that controls the refining bottleneck for a handful of obscure elements can quietly control which other countries get to build advanced technology at all, without ever firing a shot or issuing a formal policy statement. It was a preview. What has happened since 2023 has been the main event, and this time the target hasn't been one country's electronics sector. It's been the defense and clean energy supply chains of the entire Western world at once. In April of 2025, in direct response to new American tariffs on Chinese goods, China's Ministry of Commerce announced export controls on 7 rare earth elements and a range of products containing them, requiring special licenses before Chinese origin rare earth material or magnets built from it could leave the country. Exports of the restricted elements and finished magnets dropped sharply within weeks. Then, in October of that same year, Beijing escalated further, issuing a rule that reached far beyond simple export licensing. The new controls asserted authority over foreign-made products anywhere in the world that contain a meaningful share of Chinese origin rare earth material, and specifically targeted companies with ties to foreign militaries, effectively threatening to deny export licenses to firms connected to the United States defense industry starting in December. For a supply chain that touches nearly every advanced weapon system in the American arsenal, that wasn't a subtle warning. It was a demonstration of exactly how much leverage one country had accumulated over technology it doesn't itself build, simply by controlling the raw material and the refining almost everyone else depends on. Washington's answer to that leverage hasn't been limited to speeches. Buried inside 2 consecutive defense authorization bills, lawmakers wrote a hard deadline into law. Starting on the 1st of January 2027, the Department of Defense will be prohibited from using samarium cobalt magnets, neodymium iron boron magnets, and several related metals and alloys in any weapon system if any stage of their production, from mining through refining through the final melting of the metal, happened inside China, Russia, Iran, or North Korea. A narrower version of that same rule, covering the final stages of metal production, is already in effect through the end of this year. Waivers exist on paper for cases where no viable alternative source can be found, but they are meant to be the exception, not the routine. Evaluated case by case, rather than granted automatically, and by the government's own accounting, there's currently no fully scaled, fully domestic mine-to-magnet supply chain anywhere in the United States capable of meeting that deadline on its own. That's the ticking clock sitting underneath everything happening in Wyoming right now. It isn't an abstract concern about some future scenario. It's a legal deadline, already written into federal law, that the country's entire defense manufacturing base is racing against. With roughly a year left on the clock and only a handful of domestic projects, Mountain Pass among them, anywhere close to being ready, which is exactly why a still unproven pilot project in Wyoming gets treated with a level of federal urgency that a normal, early-stage mining venture almost never receives. All of this urgency traces back to a fairly dry piece of federal law that most Americans have never heard of, and pulling back the curtain on it helps explain why a small, unproven mining project in Wyoming gets treated with a level of federal attention that an ordinary early-stage mine never receives. Back in 2020, Congress passed a broad energy policy bill that, among many other things, directed the government to formally define and publish a list of what it calls critical minerals, raw materials essential to the country's economic or national security, that also face a real risk of supply disruption, and for which no easy substitute exists. The United States Geological Survey maintains that list and updates it periodically, and it currently runs to roughly 50 different minerals and elements, everything from lithium and cobalt, essential for batteries, to gallium and germanium, essential for semiconductors, to antimony, essential for ammunition and flame retardants, alongside all 17 rare earth elements. Landing on that list isn't just a symbolic honor, it's a legal trigger. It can unlock faster environmental review under a federal coordination program called FAST-41, the same program that Wyoming's other rare earth project, Bear Lodge, is moving through even as it remains stuck in the review process after more than a decade. And critically, it can unlock direct federal funding under Title III of the Defense Production Act, a Korean War-era law that gives the president authority to directly invest in, or even directly purchase output from, private companies producing materials the country decides it can't afford to be without. That authority isn't hypothetical. The Department of Defense has already used it repeatedly on exactly this industry. In 2020, it awarded MP Materials roughly $9.6 million under that program to build out light rare earth separation capability at Mountain Pass, the step that let the mine stop shipping raw concentrate to China for processing. 2 years later, it followed up with a much larger award, roughly $35 million, specifically to build heavy rare earth processing capacity, the harder, more expensive half of the separation problem. Lynas, the Australian company running the Malaysian processing plant, received its own Defense Production Act award as well, roughly $30 million, to help build a separate light rare earth separation facility on American soil in Texas, meaning the government has been quietly underwriting pieces of all three major non-Chinese rare earth efforts, Mountain Pass, Lynas, and now, through its cooperative research agreement, Brook Mine, rather than betting everything on a single company or a single deposit. A more recent presidential order has gone further still, formally determining that critical minerals and the magnets built from them meet the legal threshold for this kind of direct federal investment, opening the door to move faster and write larger checks the next time a project like this needs one. None of this is charity, and none of it's really about Wyoming specifically. It's closer to an insurance strategy, spreading federal support across multiple projects, multiple companies, and multiple kinds of deposit, on the theory that at least one or two of them need to succeed for the country to hit that 2027 defense deadline with anything real to show for it. Brook Mine happens to be one of the deposits that critical mineral bundling helps the most, because it doesn't just carry rare earths. It carries meaningful quantities of scandium and gallium alongside them, both separately listed as critical minerals in their own right, both useful in aerospace alloys and semiconductors respectively, and both valuable enough that mining them as a byproduct alongside the rare earths can materially improve the economics of the whole operation. The same way a copper mine can sometimes turn a profit on the gold and silver riding along with the copper. The scale of what that deadline is protecting is hard to overstate once you look at where rare earth magnets actually end up. A single F-35 fighter jet is estimated to require somewhere in the range of 400 kilograms of rare earth material across its magnets, radar systems, and targeting electronics, which is roughly the weight of 3 grown adults, packed into magnets small enough to fit inside a single aircraft's actuators and radar array. Submarines, Tomahawk cruise missiles, Predator drones, and the guidance systems on Patriot and Standard missile interceptors all depend on the same narrow family of magnets. Newer programs under development lean on the same supply just as heavily. Swarms of low-cost autonomous drones envisioned under a Pentagon initiative called Replicator, and a proposed multi-layered missile defense shield known as Golden Dome, both require enormous numbers of precisely manufactured, defense-grade magnets, and both are running into the same bottleneck. Qualified magnets that meet strict domestic sourcing rules are in desperately short supply, and the Pentagon gets priority access ahead of the commercial market whenever the two compete for the same limited output. On the civilian side, insane demand is climbing just as fast for entirely different reasons. Rare earth magnets used specifically in electric vehicle drive motors accounted for an estimated 37,000 tons of demand in 2024, projected to climb past 40,000 tons within a year, and demand for the core group of magnet-grade rare earths overall has roughly doubled since 2015, with further growth of about a third expected by 2030 under current policy trends. Every offshore wind turbine installed with a direct drive generator, a design increasingly preferred because it needs less maintenance out at sea, where a technician can't simply pull over and pop the hood, adds more magnet demand on top of that, and a single modern offshore turbine can stand taller than a 50-story building, with a generator at its peak that can weigh several hundred tons. There's a broader lesson sitting underneath all of this about how a modern supply chain actually breaks, and spelling it out, explains why officials in Washington treat a shortage of a few thousand tons of an obscure metal as seriously as they treat a shortage of something obviously massive like oil or steel. A single electric vehicle can contain tens of thousands of individual parts, and a single fighter jet contains vastly more than that. But neither vehicle needs every one of those parts to be scarce before production grinds to a halt. It only needs one. The world got a real, painful demonstration of that exact dynamic during the semiconductor chip shortage of the early 2020s, when a relatively small, specialized category of electronic components, worth a tiny fraction of a finished vehicle's total value, halted assembly lines at nearly every major automaker on Earth for the better part of 2 years, simply because there was no substitute available at the volume the industry needed. Rare earth magnets sit in exactly that same structural position inside an electric motor, a missile guidance system, or a wind turbine generator. A small component by weight and by cost, an irreplaceable one by function, and one that, unlike a computer chip, currently has almost no domestic manufacturing capacity standing behind it if the primary foreign supplier decides to slow the tap. That's the real shape of the vulnerability Brook Mine and projects like it are trying to patch. Not a shortage of some bulk commodity that could be stockpiled cheaply in advance, but a shortage of one small, specific, currently irreplaceable link sitting near the front of an enormous number of supply chains at once. The wind turbine side of this demand story deserves one more moment, because the underlying physics is almost the exact mirror image of the electric motor described earlier, and seeing that mirror makes the whole magnet story click into place a little more completely. A motor takes electricity and uses a magnetic field to produce spinning motion. A generator runs the same relationship backward, taking spinning motion, in this case a turbine blade assembly, caught by ocean or prairie wind, and using a magnetic field to produce electricity instead. Older wind turbine designs relied on a gearbox to step up the relatively slow rotation of the blades into the much faster spin a conventional generator needs, a mechanically complex, maintenance-heavy piece of equipment that also happens to be a frequent point of failure in a wind farm, especially one sitting miles offshore where a repair crew can't simply drive out with a wrench. A direct drive design skips the gearbox entirely, spinning a much larger permanent magnet generator directly off the slow-turning blade hub. And the only realistic way to build a generator that large, that heavy, and still efficient enough to be worth the engineering trade-off is with rare earth magnets strong enough to do the job without needing the mechanical amplification a gearbox otherwise provides. That's why the offshore wind industry in particular, chasing fewer maintenance trips out to remote turbines sitting far out at sea, has leaned so heavily into a design that depends almost entirely on the same neodymium, praseodymium, dysprosium, and terbium supply chain already stretched thin by defense programs and electric vehicles. 3 completely different industries, propulsion, defense, and power generation, all converging on the same narrow shelf of the periodic table for reasons unconnected to one another except the physics of a strong, stable, permanent magnet. Prices have reacted the way you'd expect scarcity and geopolitical risk to make them react. The price of neodymium praseodymium oxide, the workhorse combination behind most high-performance magnets, has roughly doubled since December of 2024. A gap has also opened up between materials secured under domestic and allied arrangements and material priced for open export out of China, with buyers now willing to pay noticeably more for supply that can't simply be cut off by a policy announcement in Beijing. Essentially a security premium layered directly on top of the ordinary cost of the metal itself. That dynamic is exactly why, earlier in 2025, the Department of Defense struck a landmark deal with MP Materials, guaranteeing a price floor of roughly $110 per kilogram for neodymium praseodymium oxide over a 10-year period, essentially the federal government underwriting domestic production because the open market on its own had not made that production reliably profitable. The exact same market dynamic that killed Molycorp a decade earlier. A price floor like that's in effect an insurance policy against the exact kind of price war that once emptied out Mountain Pass. And it signals plainly that Washington has decided it won't let that particular history repeat itself without a fight. Step back far enough, and the reason all of this is colliding at once, right now, in this particular decade, becomes clearer. Two enormous, largely unrelated global projects happen to be racing through the exact same narrow supply bottleneck at the exact same time. The first is the clean energy transition, the build-out of electric vehicles and wind power that governments and automakers have committed trillions of dollars toward over the coming years, all of it leaning on the same handful of magnet-grade rare earths. The second is a defense buildup happening largely in response to rising tension with the very country that controls most of the world's rare earth refining, a buildup that leans on those same elements for radar, missiles, drones, and next-generation interceptor systems. Under ordinary circumstances, a civilian industry and a military industry competing for the same raw material might not create much friction, since defense demand has historically been a small slice of overall rare earth consumption. What has changed is that both demands are climbing steeply at once, at precisely the moment the primary supplier of the material both depend on has started treating access to it as a lever of geopolitical leverage rather than simply a commercial transaction. Picture what a serious, sustained supply disruption would actually mean on the ground, based on what has already happened during the smaller shocks of the last 2 years, rather than pure speculation. Automakers who can't secure enough neodymium praseodymium magnets don't simply pay more, though they do that too. They redesign motors around less efficient alternatives, delay vehicle launches, or in some documented cases, during the 2025 export slowdown, idled specific production lines for days or weeks at a time while suppliers scrambled for compliant material. Defense contractors facing the same shortage can't simply substitute a different metal into a guidance system that's already been engineered, tested, and certified around a specific magnet's exact performance characteristics. Requalifying a new material inside a weapon system already fielded or in late-stage development can take years, not months, which is precisely why the 2027 deadline written into law has generated so much anxiety inside the defense industrial base rather than being treated as a routine compliance date. Analysts who study this supply chain closely have been blunt about the exposure. A handful of critical weapons programs, along with enormous swaths of the civilian electronics and clean energy sectors, currently have no fully qualified, fully domestic path around a determined Chinese export restriction, which is exactly the vulnerability that a still unproven pilot plant outside Sheridan, Wyoming, has been asked to help close, one small piece at a time, alongside Mountain Pass, alongside Linus, and alongside whatever the next coal country drill hole eventually turns up. That's the actual scale of the bet being placed on a few thousand acres of Wyoming clay. Not that Brook Mine alone solves American rare earth independence, because no single project realistically could, but that it becomes one more working piece in a supply chain the country is trying to rebuild from nearly nothing under a legal deadline, while its main strategic rival controls most of the alternative. Congress's own watchdog has been sounding a version of this alarm for years through unglamorous but influential channels. The Government Accountability Office has repeatedly examined the Pentagon's exposure to rare earth and critical mineral supply disruptions in its reporting to lawmakers, consistently flagging the absence of a fully mapped, fully secured domestic supply chain as a genuine national security gap, rather than a routine procurement inconvenience, the kind of finding that tends to sit quietly in a government report until a moment like this, one gives it sudden political weight. That's worth remembering the next time this story gets told with more drama than it actually needs, because nothing about it requires exaggeration to matter. This was never a mystery in the sense of something unknowable or uncanny. It was an ordinary, explainable gap between what a piece of Wyoming clay actually contained and what anyone had ever bothered to measure, sitting inside a country that had also, separately and for entirely rational reasons, spent years growing anxious about exactly the kind of material that clay turned out to hold. Two ordinary facts, one geological and one geopolitical, happened to collide at the same coordinates on a map, and the collision is the entire story. Nothing about it needed to be strange, to be significant. All of that's the backdrop. Now here's where Wyoming actually enters the picture, not as a policy abstraction, but as a specific piece of ground that nobody planned on mattering this much. A company called Ramaco Resources is, at its core, a coal company. It bought an old, mostly worked-out mine near the town of Ranchester back in 2011, the kind of property with a mining history stretching back to the 1800s and a name, the Brook Mine, that meant nothing to anyone outside the region. For years, the company did what coal companies do. It drilled exploration holes, logged the rock, tested the coal quality, and planned around the coal seams themselves. That testing focused on a narrow set of properties: heat content, ash percentage, moisture, and sulfur. The handful of measurements that determine whether a coal seam is worth mining and what it'll be worth once burned. None of those standard tests were ever designed to detect rare earth elements, which typically show up in concentrations measured in parts per million, far too faint for ordinary coal-quality instruments to notice, and far outside what anyone in that line of work was even looking for. The clay layers sitting above and below the coal seams were treated the way they are treated at almost every coal mine in the country, which is to say they were barely treated at all. They were overburden, waste rock, something you move out of the way to get to the product you actually came for. What changed was a decision to send some of that waste rock out for a broader chemical analysis, using a far more sensitive technique called inductively coupled plasma mass spectrometry, an instrument capable of detecting elements down to a few parts per billion, by essentially vaporizing a tiny sample into a superheated plasma, hotter than the surface of the sun, and sorting the resulting ions by mass one at a time. That isn't a test anyone runs on ordinary coal waste rock as a matter of routine, because it's expensive and because nobody expects the answer to be interesting. Somebody at Ramaco ran it anyway, partly out of curiosity about the mine's overall mineral content, and scientists at the Department of Energy's National Energy Technology Laboratory confirmed the results. The numbers didn't look like ordinary coal country clay. They looked like a rare earth deposit. By May of 2023, Ramaco was standing in front of investors describing something almost nobody in the American mining industry had expected to hear that year: a major deposit of magnetic rare earth elements sitting inside, above, and below the coal seams of a mine that had been operating, in one form or another, for well over a century. The geology behind that surprise turns out to be almost as interesting as the discovery itself, and it rewards a closer look because it explains why a mine could sit on top of this material for 130 years and never notice. Most of the world's historically important rare earth deposits, including Mountain Pass, are what geologists call hard rock deposits formed by unusual igneous rocks called carbonatites, essentially frozen remnants of ancient volcanic plumbing where rare earth-bearing minerals crystallize directly out of molten rock over millions of years. Wyoming has one of those too, sitting elsewhere in the state near the town of Sundance, in a mountain range called the Bear Lodge Mountains. Prospectors first worked that district back in 1875, chasing gold, and only decades later, once modern rare earth exploration picked up renewed interest around 2009, did geologists recognize the carbonatite there as one of the largest and richest rare earth occurrences in North America, later confirmed by the United States Geological Survey as a world-class deposit. And yet more than 15 years after that renewed interest began, The Bear Lodge project is still sitting in federal permitting, officially designated a covered project under a program meant to speed up exactly this kind of review, but still years away from producing a single ton of finished material. Knowing a deposit exists and getting it into production, it turns out, are two very different timelines, shaped as much by permitting, financing, and processing chemistry as by how much rare earth is actually sitting in the rock. There's a specific, practical reason Brook Mine managed to move from discovery to an operating mine in roughly 2 years, while Bear Lodge has spent over a decade stuck in review. And it's less to do with political favoritism and more to do with the accident of what kind of ground each project started on. Opening an entirely new mine in the United States on previously undisturbed federal or private land typically means years of environmental review under the National Environmental Policy Act, baseline wildlife and water studies, public comment periods, and often litigation from opponents, a process that mining industry advocates have long complained can stretch past a decade before a single shovel touches undisturbed ground. Precisely the kind of timeline Bear Lodge has been living through. Brook Mine largely sidestepped that entire gauntlet because it was never a new mine in the regulatory sense at all. Ramaco already held an active coal mining permit on that ground for a coal seam that had been legally approved for extraction years earlier, complete with the environmental baseline work, water rights, and land disturbance approvals that process requires. Adding rare earth and critical mineral recovery to an already permitted coal operation is a fundamentally smaller regulatory lift than starting a brand new mine from bare ground, closer to amending an existing permit than applying for one from scratch. That distinction, an old, already approved coal mine simply expanding what it extracts from ground it was already legally entitled to disturb rather than a new mine breaking undisturbed land, is a large part of why Wyoming's unconventional deposit reached production so much faster than its conventional cousin ever has. And it's a genuine structural advantage that any future coal country rare earth discovery, if the Department of Energy's broader hypothesis about coal country holds up elsewhere, would likely be able to lean on as well. Brook Mine is a different animal from Bear Lodge entirely, and the industry has taken to calling deposits like it unconventional for exactly that reason. Roughly 60 million years ago, during the geological period called the Paleocene, this part of Wyoming wasn't a coal mine at all. It was a warm, swampy lowland, closer in character to a coastal wetland than to the high, dry plains sitting there today. The kind of environment that slowly compresses dead vegetation into peat, and given enough time and burial, into coal. Every so often, volcanic activity somewhere in the region, likely tied to mountain building happening elsewhere in the western United States at the time, sent clouds of fine ash drifting over that swamp. And the ash settled into thin layers sandwiched between the accumulating plant material, layer after layer, ashfall after ashfall, over a span of time longer than the entire history of primates on Earth. Volcanic ash happens to carry a modest but real concentration of rare earth elements locked inside its glassy structure. Over the following tens of millions of years, groundwater percolating through those ash layers slowly broke the glass down into clay minerals, and as it did, it appears to have redistributed and, in places, concentrated the rare earth atoms riding along inside it, adsorbing them onto the surfaces of newly formed clay particles, the way a sponge picks up dissolved minerals from water passing through it, patiently, invisibly, for longer than anyone can really picture. The result is a deposit where the valuable material isn't locked inside hard crystal structures that require blasting and crushing tons of rock to liberate. It's loosely bound to soft clay, chemically similar in principle to a style of low-grade ion adsorption clay deposit that's quietly supplied the majority of the world's heavy rare earths out of southern China for decades, concentrated especially in Jiangxi province, where more than half of China's own reserves of this style sit. That similarity is exactly why it's significant, and also why it deserves a note of caution rather than pure celebration. If the clay at Brook Mine behaves the way southern Chinese clay deposits behave, it may eventually be possible to leach the rare earths out using comparatively mild chemistry, typically an ammonium sulfate solution poured through the clay to displace the adsorbed rare earth ions and carry them out in solution, rather than the industrial-scale acid processing that hard rock ore usually demands. That'd be a meaningfully cheaper, meaningfully faster path to production. It hasn't historically been a clean one. Decades of that same leaching technique in southern China have left a documented trail of contaminated groundwater and soil, with ammonia nitrogen levels in some tailings still measured many times higher than background levels more than a decade after mining stopped in certain sites, and elevated rare earth concentrations lingering in surface water near old mining areas long after production ended. Whatever process Ramaco ultimately settles on for Wyoming will have to reckon with that same chemistry, under considerably stricter American environmental regulation than exists across most of rural southern China, and whether it can do so cheaply enough to be profitable, while avoiding the same contamination is still an open engineering question rather than a solved one. Picture what the pilot plant rising outside Sheridan is actually built to do, because the phrase processing facility can sound abstract next to the drama of a rare earth discovery, when in practice it describes a fairly specific, fairly unglamorous sequence of industrial steps. Coal and the surrounding clay come out of the ground together through conventional surface mining, the same kind of truck and shovel operation used across the rest of the Powder River Basin, rather than any exotic new mining method invented for this deposit. The rare earth-bearing clay gets separated out and fed into the pilot circuit, where it's expected to be mixed with a leaching solution, likely some variation of the ammonium sulfate chemistry already used in southern China, designed to pull the loosely bound rare earth ions off the clay particles and into a liquid that can actually be handled, filtered, and processed further. From there, the plan calls for concentrating that rare earth-bearing solution and beginning the separation work, isolating individual elements from one another using the same underlying solvent extraction principle described earlier, just built at a much smaller, test-scale footprint designed to prove the chemistry works on real Wyoming material before anyone commits the far larger sum of money a full commercial-scale refinery would require. Every ton that moves through that small pilot circuit generates real data. How much rare earth actually gets recovered out of the clay? How much reagent gets consumed doing it? How the resulting waste needs to be handled and disposed of safely under Environmental Protection Agency and Wyoming state regulations, and how consistent the ore grade turns out to be as mining moves across different parts of the property. None of that data exists yet in a form anyone can fully trust, which is exactly why the preliminary economic assessment built by Fluor carries the caveats it carries, and exactly why the middle of 2026 matters so much as a date. It isn't simply a ribbon-cutting milestone. It's the point at which Brook Mine's economics stop being a spreadsheet exercise and start being something measured directly off real Wyoming rock, tested at Wyoming's own chosen chemistry, under Wyoming's own regulatory rules. None of that geology was visible to the naked eye back when this was simply a coal mine. A driller pulling a core sample out of that clay layer sees gray rock, not glowing rock, not obviously strange rock. That's the actual mechanism behind the word hidden in this story. Nothing about this deposit is supernatural or unexplainable. It was invisible because nobody had ever pointed the right instrument at it, and it stopped being invisible the moment somebody finally did. It also wasn't entirely without warning, if you knew where to look nationally, rather than just locally. Years before anyone drilled a rare Earth-specific hole at Brook Mine, the Department of Energy had already been quietly funding research into exactly this possibility across American coal country. Starting around 2015, The department's National Energy Technology Laboratory launched a multi-year research effort specifically to test whether coal ash, and even the acidic wastewater that drains out of old coal mines might hold recoverable concentrations of rare earth elements. Researchers at West Virginia University, sampling acid mine drainage sludge from bituminous coal mines across the Appalachian Basin, found that the sludge held on average roughly 2,600 times the rare earth concentration of the raw drainage water itself. A striking demonstration that decades of coal mining had been inadvertently concentrating these elements into waste streams the whole time, right alongside the coal everyone actually came for. The University of Kentucky ran parallel pilot-scale work aimed at extracting usable rare earth oxides from similar feedstocks. Beyond those two lead institutions, the department funded mineral processing research at more than a dozen universities scattered across the country, including, worth noting, the University of Wyoming itself. Years before Brook Mine's own discovery made national headlines, none of that federally funded research happened to land directly on the clay at Brook Mine before Ramaco's own testing did. But it means the underlying idea that American coal country might be sitting on an overlooked rare earth resource wasn't a lucky guess invented after the fact. It was a hypothesis serious government scientists had already been testing for the better part of a decade, waiting for exactly the kind of confirmation Ramaco's clay eventually provided, which is a large part of why the National Energy Technology Laboratory was able to move so quickly once Ramaco's samples landed on its desk. They weren't starting from zero. They already knew, in principle, exactly what to look for. Once Ramaco knew what it was sitting on, the obvious next question was how much of it there actually was, and that number has been climbing steadily ever since, which tells its own story about how early this discovery still is. The first serious estimate, based on initial testing across a section of the mine, put the deposit at somewhere between roughly 640,000 and 800,000 tons of what the industry calls total rare earth oxide, or TREO, essentially the combined weight of every rare earth element present, measured as if it were already in oxide form with no minimum concentration cutoff applied. As drilling expanded, that number moved to about 1.2 million tons. A later technical report pushed it further, to roughly 1.5 million tons. By the most recent assessment available, the high-end estimate had climbed again, to approximately 1.7 million tons of total rare earth oxide, including meaningful quantities of two additional critical minerals, scandium and gallium, that tend to travel alongside rare earth deposits and carry their own strategic value, together making up somewhere around a sixth of the entire figure. Notice how that number grew, because it matters almost as much as the number itself. In most mining exploration, additional drilling tends to sharpen and often shrink an early estimate, as optimistic early assumptions get tested against harder data. Here, each of those estimates came from drilling a larger portion of the property and running more samples through the lab. And each time the company looked harder, the deposit got bigger rather than smaller, suggesting the mineralization actually extends further across the property than early testing alone could show, rather than simply reflecting more generous assumptions. And even that 1.7 million ton figure only reflects analysis of about 4,500 acres out of a permitted area covering roughly 15,800 acres, meaning less than a third of the property has actually been tested. More than 120 core holes have now been drilled specifically targeting rare earth elements across 3 separate drilling programs, and the honest answer to how large this deposit ultimately is remains unknown, not because anyone is hiding it, but because the drilling required to know for certain simply hasn't happened yet across most of the ground. Every additional hole either confirms the pattern seen so far, in which case the resource likely keeps growing, or it hits a natural edge where the ashfall clay thins out or disappears, in which case the estimate finally settles somewhere close to its true size. Nobody yet knows which of those two outcomes the remaining acreage holds. The possibility that this number moves in the other direction deserves equal weight, since a fair accounting of an evolving resource estimate has to hold both possibilities at once. The 4,500 acres tested so far weren't chosen at random. Exploration programs typically start by drilling the ground geologists already suspect looks most promising, based on surface geology, earlier coal exploration data, and whatever encouraging early results come back first, which means the untested two-thirds of the property isn't guaranteed to hold rare earth-bearing clay of the same thickness or grade as the ground already confirmed. Ashfall layers by their nature can thin out, pinch off entirely, or shift in composition as you move across a 60-million-year-old landscape that was never uniformly flat or uniformly swampy to begin with. It's entirely possible that further drilling confirms a rich, continuous deposit across the full permit area. And it's also entirely possible that the richest material sits concentrated in the section already tested, with the surrounding ground holding a thinner, lower-grade version of the same clay. Nothing in the public record currently answers that question either way, and it won't be answered by public statements or press releases. It'll be answered the same way every previous estimate got revised. One drill hole, one lab result, and one technical report at a time. Within that total, not every rare earth element carries the same value. The magnet-grade elements, neodymium, praseodymium, dysprosium, and terbium, the ones that go into the high-performance permanent magnets driving electric motors and wind turbine generators, make up roughly a quarter to a third of the total tonnage identified so far. An economic assessment commissioned from the engineering firm Fluor Corporation, working alongside a materials testing firm called Hazen Research to design the actual processing and refining flow sheet, put a dollar figure on the broader resource, estimating the material's value at somewhere in the neighborhood of $37 billion, a figure roughly comparable to the entire annual state budget of Wyoming several times over, and separately calculated a net present value for a mining and processing operation of roughly $1.2 billion, assuming an 8% discount rate, with an internal rate of return estimated near 38% before taxes. Under that plan, the operation was initially projected to produce a little over 1,200 tons of rare earth and critical mineral oxides per year, a figure the company has since revised sharply upward to more than 3,400 tons annually, an increase of roughly 175%, as further drilling improved confidence in the size and grade of the resource. Even that upgraded figure is modest set against a facility like MP Materials' magnet plant in Texas, which alone is built to consume roughly 1,000 tons of finished magnet material a year, a reminder that a successful Brook mine would still be one contributor among several needed to fill the gap the country is racing to close before that 2027 deadline arrives, rather than a single solution capable of closing it alone. It helps to actually hold some of these numbers up against something familiar, rather than letting them float past as abstractions. 4,500 acres, the portion of Brook Mine tested so far, covers roughly 7 square miles, an area you could walk across in an afternoon, smaller than many mid-sized American towns. The full 15,800-acre permit area runs closer to 25 square miles, still a patch of ground you could drive the length of in well under an hour. And the entire known deposit sits inside that single, modest rectangle of Wyoming grassland rather than sprawling across some vast, unmappable region. 1.7 million tons of total rare earth oxide sounds enormous until you remember how thin the useful magnet-grade slice actually is. Roughly a quarter to a third of that figure, once cerium, lanthanum, and the other lower-value elements in the mix are set aside. Even at the company's most optimistic mature production rate, a little over 3,000 tons of finished oxide leaving the site each year, that magnet-grade fraction alone, translated all the way through to finished metal and magnet, could plausibly support the neodymium iron boron content inside something on the order of a few 100,000 electric vehicle motors annually. A meaningful contribution to domestic supply without coming remotely close to satisfying it alone, since American EV production alone is measured in the millions of vehicles each year and climbing. Put simply, a fully successful Brook mine would be a genuine and useful addition to the country's supply, not a solution that makes the rest of this story unnecessary. There's a precise technical distinction buried inside mining terminology that's worth making explicit, because casual coverage of this story tends to blur it in a way that quietly overstates how far along the project actually is. Everything described so far, the 640,000 tons, the 1.2 million, the 1.5 million, and the current 1.7 million ton figure, is what the industry calls a resource estimate, a technically informed calculation of how much material is believed to exist in the ground based on drilling density, sample assays, and geological modeling. It isn't the same thing as a reserve, a narrower and considerably more rigorous category reserved for the portion of a resource that a detailed feasibility study has confirmed can actually be mined and processed at a profit, under a specific mine plan, at specific assumed prices, with all the engineering and permitting risk accounted for. Brook Mine, as he says, Brook Mines as of now has a resource estimate and a preliminary economic assessment. It doesn't yet have a formally classified reserve because the bankable feasibility study that'd produce one hasn't been completed, and normally wouldn't be completed until the pilot plant has generated enough real operating data to support it. That gap between resource and reserve is exactly where a meaningful share of mining projects worldwide quietly stall out, when rock that looked promising on paper turns out to be too expensive, too inconsistent, or too complicated to extract profitably once engineers run the real numbers. None of that means Brook Mine will fall into that category. It means the honest, technically precise status of the project right now is promising and unproven at once, a resource waiting to earn its way into becoming a reserve, rather than a deposit whose economics have already been locked in. The two critical minerals riding along with Brook Mine's rare earths, scandium and gallium, aren't incidental details either, because China had already shown its willingness to weaponize exactly that part of the periodic table before it ever touched rare earths directly. Back in the summer of 2023, months before Ramaco's own discovery became public, China announced that gallium and germanium, two minerals essential to semiconductor manufacturing, fiber optics, and infrared night vision equipment, would require a special export license to leave the country, a direct response to earlier American restrictions on advanced chip-making equipment sold into China. It wasn't a full ban, but it forced every buyer of those materials outside China to disclose exactly who they were, what they intended to use the material for, and to wait on a licensing process controlled entirely by Chinese officials, since China supplies the overwhelming majority of the world's refined gallium and a similarly dominant share of refined germanium. Seen against that backdrop, a Wyoming clay deposit that happens to carry meaningful gallium alongside its rare earths isn't just a lucky bonus for Ramaco's balance sheet. It's one more small crack in a second, closely related choke point that Washington has been just as anxious about as rare earth magnets themselves, keeping the actual scale of Brook Mine honest against the country's one fully operating conventional rare earth mine, rather than letting the size of the dollar figures alone create an impression of parity that doesn't yet exist. Mountain Pass, running at full commercial scale, with more than a decade of continuous operating history behind its current ownership, produced over 50,000 tons of rare earth material in concentrate form in 2025 alone, a 12% increase over the year before. Brook Mine's own mature production target, even after being revised upward, sits at a little over 3,000 tons of finished oxide a year, a meaningfully different stage of processing and a considerably earlier point on the production curve, but still a useful reminder of just how much larger and more established the country's existing rare earth operation remains. Brook Mine isn't yet competing with Mountain Pass. It's trying to become a second, meaningfully smaller node on a supply chain that, right now, still runs through essentially one American mine, one Australian mine, and whatever fraction of the market the rest of the world can pry away from Chinese refining capacity in the years immediately ahead. Those figures deserve a healthy dose of caution, and it's worth being upfront about exactly where that caution belongs. What Fluor produced is what the mining industry calls a preliminary economic assessment, an early-stage estimate meant to gauge whether a project is worth pursuing further, built on assumptions about future commodity prices, construction costs, and recovery rates that haven't yet been tested by a full feasibility study or years of actual production data. It's a real step, built by an outside engineering firm rather than by Ramaco itself, but it sits several rungs below the kind of bankable, fully de-risked study that lenders typically require before financing a mine at massive scale, and the pilot processing plant now under construction exists specifically to close some of that gap, generating the real-world recovery rates, energy costs, and reagent consumption data that a later, more rigorous feasibility study will eventually need. A resource estimate isn't a guarantee of profit. It describes what's believed to be in the ground based on the data collected so far, not what a company will actually succeed in extracting, processing, and selling at a profit years from now. The scale of this deposit appears to be real, confirmed by an independent federal laboratory rather than only by the company that stands to profit from it. Whether that scale ever translates into the kind of production the early numbers imply is a separate question, one that'll only be answered by years of drilling, engineering, and construction still ahead, and the history of this exact industry, from the Mountain Pass boom and bust to the long list of promising rare earth juniors around the world that raised money, drilled encouraging holes, and never produced a single commercial ton, argues for exactly that kind of patience. Assuming the pilot plant does succeed at the scale and cost its backers expect, the path forward from there follows a fairly well-worn industry sequence, even if the specific dollar figures and timeline for Brook Mine's version of it aren't yet public. A successful pilot generates the real-world recovery rates, reagent costs, and waste handling data needed to support a full, bankable feasibility study. The document lenders and larger institutional investors typically require before committing the hundreds of millions or billions of dollars a full commercial-scale refinery actually costs to build. That feasibility study, assuming it comes back favorable, would then support financing for a considerably larger processing facility, likely built in phases, each one scaled to match growing confidence in the resource and growing demand from customers willing to sign long-term supply contracts, the same kind of contract General Motors already signed with MP Materials years before that company's magnet factory ever produced a finished product. It's a slow, expensive, capital-intensive sequence by design, meant to catch exactly the kind of over-promising that sunk other rare earth juniors before a single dollar of debt gets committed to a facility that might not work as planned. Nothing about Brook Mine's federal backing or its accelerated political timeline changes that underlying sequence. It can compress the calendar between each stage, and it appears to already be doing exactly that, but it can't skip a stage entirely without taking on a level of financial risk that neither Ramaco's lenders nor the federal government backing this project has shown any appetite for so far. Add up every dollar figure scattered through this story so far, and a clearer picture of the moment we are actually standing in starts to emerge. One measured in already committed capital rather than only in speculative resource value. Ramaco's own $200 million stock offering, Wyoming's $6.1 million state grant, the federal government's $9.6 million and $35 million Defense Production Act awards, that rebuilt separation capacity at Mountain Pass. A further $30 million in Defense Production Act funding that helped Lynas establish its own separation facility on American soil. A $1 billion-plus expansion already underway at MP Materials' Texas Magnet campus. A 10-year federal price guarantee designed specifically to keep that entire ecosystem from collapsing the way Molycorp once did. None of these figures were spent on the same project, and none of them alone would look like much next to the size of a modern national budget. Stacked together, though, they describe something that didn't exist 5 years ago. A real, if still fragile, financial commitment spread across multiple companies, multiple states, and multiple federal agencies, all pointed at the same narrow goal of building an American rare earth supply chain that can't be shut off by a single foreign policy decision made in Beijing. Brook Mine is one piece of that stack, not the whole of it, and probably not even the largest piece of it. But it's the piece sitting on ground nobody thought to look at closely until 3 years ago, which is exactly why it's become the piece most people are still learning the name of. All of that national-level strategy eventually has to land somewhere on a map. And in this case, it lands on a fairly small, fairly quiet corner of northern Wyoming, where the consequences are considerably more local and considerably more human. Sheridan sits along the eastern edge of the Bighorn Mountains, on the northern fringe of the Powder River Basin, the single largest coal-producing region in the entire country, a landscape of open high plains that runs up against a wall of forested peaks rising abruptly out of the grassland. Ranchester, the small town closest to the mine itself, sits a few miles further west toward those mountains, the kind of place where the mine has functioned for generations as one of the largest local employers, rather than as an abstract economic statistic, and where a shift change at the mine gate has historically meant more to the town's daily rhythm than almost anything happening in Cheyenne or Washington. It helps to actually picture the place this is all happening in, rather than letting Wyoming stay an abstraction on a map. Sheridan County sits in the rain shadow of the Bighorn Mountains, a landscape of wide, dry grassland cut through by cottonwood-lined creeks running down out of the peaks. Winters cold enough to regularly drop well below freezing for weeks at a stretch, summers hot and dry, and distances that mean the nearest sizable city, Billings, Montana, sits more than an hour and a half away by car, and Denver sits closer to 5. This stretch of the Bighorn foothills has been inhabited for thousands of years by Crow, Cheyenne, and other Plains peoples, before it became cattle and coal country in the century following American westward expansion, and the mixture of ranching, energy extraction, and small-town commerce that defines the region today grew directly out of that longer history of people making a living off land that doesn't give much away easily. It isn't the kind of place accustomed to national attention. A ribbon-cutting ceremony at a coal mine north of a city of about 18,000 people doesn't typically draw federal laboratory scientists, national reporters, and a cabinet-level conversation about defense supply chains. And the fact that this one did says as much about how anxious Washington has become over rare earth dependence as it does about the deposit itself. The workforce transition underway at the mine is worth taking seriously on its own terms too, rather than treating it as a footnote to the geology. A great deal of what a coal miner already knows transfers directly: how to operate heavy excavation equipment safely, how to read a drill log, how to work inside a strict safety culture built around a seriously dangerous industrial environment, how to interpret core samples and communicate findings up a chain of engineers and geologists. What doesn't transfer automatically is the chemistry, handling ammonium sulfate and other reagents safely, understanding how a solvent extraction circuit behaves, running and interpreting results from analytical instruments built for parts per million precision, rather than the bulk measurements coal quality testing relies on, and managing an entirely different category of environmental compliance built around trace metal contamination, rather than coal dust and methane. That's precisely the gap Sheridan College's new training program is trying to close, turning what could otherwise be a story about coal jobs disappearing and unrelated new jobs arriving from somewhere else into a story about the same local workforce, climbing one rung up an industrial ladder it already had one foot on. Coal built roads, funded schools, and employed generations of families in this part of the state. And it's also been in a long, slow decline as utilities nationwide shift toward cheaper natural gas and renewables. A decline that's hit small, coal-dependent communities across Wyoming hard over the last decade. Cutting the tax revenue that Wyoming's counties and school districts have historically drawn from a state severance tax charged on every ton of coal, oil, and gas pulled out of the ground. A tax structure that effectively lets Wyoming run without a state income tax as long as its extraction industries stay healthy. A coal company discovering it's sitting on a critical mineral deposit worth potentially tens of billions of dollars is, for a region like this, close to the best possible version of an unlikely story. The same mine, largely the same workforce, and in some cases the same physical equipment, pivoting toward an entirely different product with an entirely different and considerably brighter growth trajectory. That pivot needed money, and it came from multiple directions at once. Wyoming's own state government, through the Wyoming Energy Authority, awarded the project a $6.1 million matching grant specifically to help fund a rare earth and critical minerals pilot processing facility. Ramaco itself raised roughly $200 million through a public stock offering explicitly earmarked to accelerate the project. Nearby Sheridan College began building out a critical minerals training program aimed at preparing local workers, some of them the same people who might otherwise have been laid off from coal jobs, for the specialized skills a rare earth processing operation actually requires, from handling reactive chemicals safely to operating the analytical instruments needed to track ore quality in real time, essentially retraining a coal workforce into a chemical processing workforce over the span of a few semesters, rather than starting from scratch with workers imported from somewhere else. In July of 2025, Ramaco held a ribbon-cutting and groundbreaking ceremony at the site, marking what the company and Wyoming's political leadership described as the first new coal mine to open in the state in more than 50 years, and, more significantly for this story, the first new rare earth mine to open anywhere in the United States in more than 70 years, going back to 1952, the same year Mountain Pass itself first began production. Local and regional coverage out of Wyoming in the months around the July groundbreaking captured a mood that was less about geology and more about relief, the sense of a region that had spent a decade bracing for coal's slow decline, suddenly being handed a strikingly different narrative to tell about its own future. State officials framed the mine as proof that Wyoming's energy economy could evolve rather than simply shrink, and pointed to it directly as evidence that the state's traditional extraction industries still had a role to play in an economy increasingly organized around batteries, motors, and defense electronics rather than furnaces and power plants. That framing runs directly against a common national assumption that coal country and the clean energy transition sit on opposite sides of an unbridgeable divide, one losing exactly what the other is gaining. Brook Mine complicates that assumption in a very literal, physical way. The same trucks, the same drill rigs, and in some cases, the same individual workers who spent a career pulling coal out of that ground are now positioned to spend the next chapter of that same career pulling out the material that keeps the very electric motors and wind turbines many coal communities have learned to resent running. Whether that reframing holds up as anything more than a hopeful headline depends entirely on the same unresolved questions already laid out here: the pilot plant's real performance, the resource's true extent, and the lawsuit's eventual outcome. But the reframing itself, a coal region betting its next chapter on the exact minerals the clean energy transition needs most, is already an unusual turn for an industry that spent the previous decade almost entirely on the losing side of that transition. There's one more layer to this story that most coverage of the rare earth discovery tends to skip past, and it changes how you should think about the coal sitting inside Brook Mine as well as the clay surrounding it. Ramaco has branded its approach to the property with the acronym CORE, short for carbon ore, rare earth, and the idea behind that name is broader than simply mining rare earths alongside coal. The company has filed more than 50 patents and pending patents around a separate proposition entirely, that the carbon inside coal itself, the same material that's been burned for heat and electricity for over a century, can instead be processed into higher value carbon materials, including graphene, carbon fiber, and graphite, the kind of advanced materials currently used in everything from lightweight aerospace components to the electrodes inside lithium-ion batteries. Graphite in particular sits on the same critical minerals list as the rare earths do, and China dominates its global supply just as heavily, refining the overwhelming majority of the material that ends up inside electric vehicle battery anodes worldwide. If that side of Ramaco's research holds up at commercial scale, and it remains considerably earlier and less proven than the rare earth side of the project, Brook Mine wouldn't simply be a rare earth mine that happens to sit inside an old coal property. It'd be a working experiment in treating an entire coal deposit as a critical minerals resource, coal, clay, and everything sandwiched between them, rather than treating coal narrowly as fuel and everything around it as waste. That reframing, more than any single number in a resource estimate, may end up being the most consequential idea this particular mine tests, because if it works, it offers every other declining coal property in the country a different reason to keep operating, and a different answer to the question of what an old coal region's future is actually for. There's a genuinely interesting political wrinkle sitting underneath all of that celebration, worth mentioning honestly rather than glossing over. Wyoming's political leadership, largely aligned with a party that's generally been skeptical of renewable energy and wind power specifically, has embraced this rare earth project with real enthusiasm, even though a substantial share of the demand driving rare earth prices upward comes directly from the electric vehicle industry and the wind turbine industry, the exact technologies that same political coalition has often criticized. It isn't a contradiction that undermines the project. It's simply a reminder that the mineral itself is politically neutral, even when the industries built around it aren't, and that a magnet doesn't care whether the motor it powers belongs to a fighter jet, an electric pickup truck, or a wind turbine spinning above the Wyoming plains. The same rare earth oxide that ships out of Sheridan bound for a defense contractor could, in principle, just as easily ship toward a wind farm developer, and nothing about the geology or the chemistry lets anyone sort the atoms by their eventual politics. Which raises a fair question. Who actually benefits if this project works the way its backers hope? The list is longer than just one company's shareholders, though they certainly stand to benefit if the resource proves out. And they also carry the most direct financial risk if it doesn't. Sheridan County gains jobs and tax revenue at a moment when coal employment has been sliding. The state of Wyoming gains a genuine diversification story, evidence that its extraction economy can pivot rather than simply decline as coal demand keeps softening elsewhere in the country. The Department of Defense gains, at least potentially, a qualified domestic source for the exact magnet materials its most advanced weapon systems depend on, materials it currently can't fully secure without exposure to a supply chain controlled by a strategic rival, and materials it'll soon be legally barred from sourcing from that rival at all. American manufacturers of electric vehicles and wind turbines gain a hedge against the kind of price spike or export restriction that's already happened twice in the last 2 years. And more broadly, the United States gains a small but real reduction in a dependence that a growing number of national security officials from both political parties now treat as an unacceptable long-term vulnerability. Set against all of that upside sits a narrower, more exposed group The investors who bought into Ramaco's stock offering on the promise of a timeline that's already drawn legal scrutiny, and the residents living closest to a processing operation whose long-term environmental footprint won't be fully known until the pilot plant has been running long enough to measure it. Fairness also means naming plainly who stands to lose ground if projects like Brookmine, Mukfrein Mountain Pass, and Linus keep succeeding, since a story about who benefits is incomplete without its mirror image. Chinese rare earth producers and, more importantly, the Chinese government's strategic leverage built on top of them lose a measure of the pricing power and geopolitical influence that decades of near-total market dominance have handed them. That isn't a small thing to concede. A market where the United States, Australia, and eventually a scattering of other allied producers can collectively supply a meaningful share of global magnet-grade rare earths is a market where an export restriction stops being an effective form of pressure, because buyers finally have somewhere else to turn even if that alternative supply costs more or takes longer to secure. That's precisely why Beijing's response to the last 2 years of Western investment in projects like this one hasn't been indifference. It's been escalation, tighter export licensing, broader extraterritorial claims over foreign-made products, and increasingly pointed rhetoric about supply chain security aimed squarely back at Washington. None of that guarantees China's dominance erodes quickly, or that Wyoming clay meaningfully dents a position built over 3 decades of sustained state investment. But it does mean the stakes on the other side of this story are exactly as real as the stakes on the American side. And it's a large part of why every step forward at Brookmine has been watched as closely from Beijing as it's been celebrated in Sheridan. Under the current administration's broader push to accelerate domestic critical mineral projects, Ramaco has said it's been asked to move faster than originally planned. And the Department of Energy's National Energy Technology Laboratory, the same lab that ran the initial analysis confirming what Ramaco had found, later signed a formal cooperative research and development agreement with the company, committing federal scientific resources to ongoing exploration, or modeling, and processing research at the site. None of that guarantees the project succeeds. It does mean that for the first time in decades, the federal government is treating an American rare earth discovery as a matter of strategic urgency rather than a niche mining story, and putting real institutional weight behind getting it built. None of that means the story is finished or that the outcome is guaranteed, and a responsible account of what's happening at Brookmine has to include the part that's still unresolved. Early this year, a shareholder lawsuit was filed against Ramaco Resources and 2 of its senior executives in federal court in the Southern District of New York, brought by a plaintiff named Lynn Henning, alleging that the company misled investors about the actual pace of progress at the project. Part of the complaint pointed to reporting from Wolfpack Research, a market research firm that publishes critical, short-seller-style analysis of public companies, which claimed that drone footage of the mine site, taken months after the widely publicized July groundbreaking ceremony, showed little visible construction activity at the location where the pilot processing plant was supposed to be rising. Ramaco has pushed back on those characterizations, stating that testing, permitting work, and site preparation were actively underway, even if visible construction had not yet reached the stage critics expected to see by that point. It'd be dishonest to pretend that lawsuit has already been resolved one way or the other, and it'd be equally dishonest to treat it as proof the entire discovery is fabricated, when the underlying rare earth analysis came from an independent federal laboratory rather than from Ramaco's own claims alone. What the lawsuit actually demonstrates is something narrower and, frankly, more useful to understand. The geology appears to be real and independently confirmed, but the timeline, the pace of construction, and the ultimate economics of turning that geology into a functioning industrial operation remain actively contested, still under litigation, and not yet proven at commercial scale. Those are two different claims, and only one of them has strong outside verification behind it right now. The honest version of this story holds both of those facts at the same time, rather than collapsing them into a single simple narrative in either direction. It's also worth remembering that Brook Mine would hardly be the first promising rare earth project to stumble on the long walk between an exciting drill result and an actual functioning refinery. Dozens of junior mining companies around the world have announced encouraging rare earth discoveries over the past 15 years, and the overwhelming majority of them are still not producing a single ton, undone by financing gaps, permitting delays, processing challenges, or all three at once. Even Mountain Pass, sitting on a deposit nobody seriously doubts, needed a full bankruptcy and a change of ownership before it found a version of itself that actually worked. And Bear Lodge, sitting on a deposit the federal government itself calls world-class, has now spent well over a decade in permitting without producing anything at all. Geology being real is necessary. It's never, on its own, been sufficient. Wall Street's own reaction to all of this has been its own kind of evidence, worth reading carefully rather than dismissing as noise. Ramaco is a publicly traded company, and its stock has moved in sharp, sometimes dramatic swings directly tied to rare earth news rather than to anything happening in its ordinary coal business, rising on encouraging drilling results and resource upgrades, and dropping hard on the short seller report and the shareholder lawsuit that followed it. That volatility isn't unusual for a small-cap mining company sitting on an unproven early-stage discovery, where a single drill result or a single critical report can swing the market's assessment of the entire company by a meaningful percentage in a single trading session. But it does tell you something real. Professional investors are treating Brook Mine as a genuine binary bet, rather than a settled outcome, pricing in real uncertainty about whether the pilot plant will hit its targets, whether the resource keeps growing as more acreage gets drilled, and whether the litigation ends up materially damaging the company's ability to raise the additional capital a full commercial-scale operation will eventually require. That kind of pricing behavior is exactly what you'd expect to see around a story that combines confirmed, independently verified geology with a still unproven path to production, and a detail worth remembering the next time a headline about the deposit's dollar value shows up without any of that surrounding uncertainty attached to it. Why did this particular convergence happen now, in this narrow window of a few years, rather than a decade earlier or a decade later? The timing turns out not to be a coincidence so much as several separate clocks all reaching the same hour at once. The geology itself set no clock at all. That clay could just as easily have been tested and understood in 1990 or 2010, and nothing about the rock itself would have been any different. What actually had to line up was everything sitting on top of the rock. The instrument capable of detecting trace rare earth concentrations cheaply enough to run as a routine test, inductively coupled plasma mass spectrometry, only became widely accessible to ordinary mining companies in relatively recent years. The federal research appetite to even suspect that coal country might hold this kind of resource only really took shape after 2015, when the Department of Energy started funding the acid mine drainage and coal ash studies described earlier. The price signal that made a company like Ramaco take a rare earth discovery seriously enough to redirect years of investment toward it barely existed before the 2010 Japan crisis, and didn't become urgent again until the price run-up beginning in 2024, and the political will to write an actual legal deadline into defense law, the kind of deadline that turns a promising discovery into a strategic priority overnight, only fully crystallized after China demonstrated, twice in 1 year, that it was willing to use export controls as a direct instrument of pressure against the American defense industrial base. Take away any single one of those pieces and this story looks very different. Without the cheaper, more sensitive lab instruments, the clay's rare earth content might still be sitting undetected today, Without a decade of quiet federal research already primed to recognize what the results meant, the discovery might have taken years longer to get taken seriously in Washington. Without the price spikes and export controls of the last 2 years, a company like Ramaco might have shelved an interesting but commercially marginal discovery rather than pouring $200 million into chasing it. And without the legal deadline now sitting on the calendar for January of 2027, a pilot plant this early in its economic life might never have attracted the kind of federal cooperation, urgency, and money that it's. Wyoming's clay didn't choose this moment. The rest of the world's dependence on a single foreign supplier finally became uncomfortable enough, all at once, for someone to go looking hard enough to find what had been sitting there the entire time. There's also a fair question hanging over Bear Lodge now that Brook Mine has changed the political weather around rare earths in Wyoming so dramatically. For more than 15 years, that carbonatite deposit near Sundance sat in the awkward position of being geologically celebrated, called world-class by the same federal survey that studies deposits like it across the entire country, while remaining commercially stalled, caught in the ordinary grinding pace of environmental review, financing rounds, and shifting rare earth prices that stalled dozens of similar projects worldwide. Nothing about the rock at Bear Lodge has changed in the years since. What has changed is the environment around it, a federal government now moving Defense Production Act money and cooperative research agreements toward rare earth projects with real urgency, a defense industry facing a hard legal deadline that didn't exist a few years ago, and a state government in Wyoming that's just watched a coal company turn an accidental discovery into a nationally covered ribbon-cutting ceremony within roughly 2 years. Whether that changed environment ends up pulling Bear Lodge through its own permitting bottleneck faster than it otherwise would have moved isn't yet answered by anything in the public record. But it's a reasonable question to keep asking, because it points at something larger than either single project. Wyoming may not end up being remembered as the place with one lucky rare earth discovery, so much as the state that happened to be sitting on two structurally different deposits at the exact moment the rest of the country finally had a reason to go looking for both of them. Change everything deserves a precise definition here, rather than letting the phrase float as pure hype, because the evidence supports a real answer without supporting an unlimited one. It almost certainly doesn't mean that a single Wyoming mine, on its own, ends American dependence on Chinese rare earth processing. Even in the most optimistic production scenario Ramaco has published, Brook Mine's output would remain a fraction of what Mountain Pass alone already produces, let alone what the country's defense and clean energy sectors consume every year and will consume in greater volume as that consumption keeps climbing through the end of the decade. What change everything can honestly mean, based on everything laid out so far, is narrower and, in its own way, more interesting. It can mean the difference between the United States having one domestic hard rock rare earth mine or two fundamentally different kinds of domestic source, hedging the entire strategy against a single point of geological or corporate failure. It can mean proving, for the first time anywhere in the country, whether America's enormous, mostly overlooked reserves of old coal ground hold a second, unconventional path to critical minerals that nobody had a reason to test before, a proof of concept that could matter far beyond Wyoming's own 15,000 acres if it holds up. It can mean giving a legally binding 2027 defense deadline one additional real option rather than zero, at a moment when the government's own assessment is that the country doesn't yet have enough qualified domestic supply to meet that deadline regardless. And for one specific corner of northern Wyoming, it can mean the difference between a slow, familiar decline as coal fades and an unlikely second act built on the very ground coal crews spent a century walking past without a second look. None of those outcomes require the deposit to be as large as its most optimistic estimate, or the company's stock price to justify every dollar of its $200 million raise, or the pending lawsuit to resolve in Ramaco's favor. They require the pilot plant to work, the chemistry to scale, and the next round of drilling to confirm what the first 3 years of testing have suggested. That's a real, meaningful, and still entirely open bar to clear, and it's a considerably more honest promise than the title's blunter phrasing might suggest on its own, without being any less significant for how much smaller and more specific it actually is. So where does that leave things right now, as this is being told? The pieces already in motion are concrete, and they are worth being precise about because this isn't a story sitting entirely in the future tense. The Brook Mine itself is open and operating, the first new rare earth mine on American soil in more than 70 years, with coal and rare earth-bearing material already being extracted to feed a processing facility under construction on site. That pilot processing plant and laboratory broke ground in the fall of 2025, following completion of local permitting, installation of high-voltage electrical power to the site, in Wombao Pais Alakawi Wombao, and the geotechnical work needed to lay its foundation. The company has stated it expects that facility to be operational by the middle of 2026, processing several tons per day of rare earth and critical mineral feedstock, the first real test of whether Wyoming clay can actually be turned into refined, sellable oxide at any meaningful scale, and by extension a real early test of whether the pace critics have questioned can turn into visible, physical results on the ground. Beyond the pilot plant, the company has proposed building what it calls a strategic critical minerals terminal directly at the site, envisioned as a national stockpiling point for rare earth and critical mineral oxides, the kind of facility that'd give the country a physical buffer against future supply shocks, rather than relying entirely on continuous, uninterrupted imports. The idea behind Ramaco's proposed strategic critical minerals terminal, a physical stockpile of refined materials sitting in reserve against a future shortage, isn't actually a new concept in American industrial policy, even if applying it to rare earths on Wyoming soil is new. The United States has built and drawn down strategic material stockpiles before, most notably during and after the Second World War, and through the Cold War decades that followed, when the government kept warehoused reserves of materials like tin, rubber, cobalt, and various strategic metals specifically because a hostile power, or simply a disrupted shipping lane, could otherwise cut off access to something the country's factories and military couldn't function without. That original stockpile system was gradually sold off and allowed to shrink across the 1990s and 2000s, in an era when globalized supply chains made the entire concept feel outdated, a Cold War relic nobody expected to need again. Rare earths are the clearest sign yet that the underlying logic never actually went away. It simply went quiet for a few decades, while a single country, China, was allowed to become the kind of choke point the original stockpile program existed to protect against in the first place. A terminal at Brook Mine, if it gets built the way Ramaco has proposed, wouldn't be resurrecting some historical curiosity out of nostalgia. It'd be rebuilding a Cold War-era tool for a newer, narrower version of the same old problem, an economy and a military that can't function without a handful of specific materials, sourced overwhelmingly from one country that's shown a repeated willingness to use that dependence as leverage. Drilling hasn't stopped either. Roughly 2/3 of the permitted acreage still hasn't been fully assessed, meaning the current 1.7 million ton estimate is very likely not the final word on how large this deposit actually is. Every additional drill hole either confirms the resource, expands it, or narrows it. And each of those outcomes changes the calculation for how significant this single Wyoming property ultimately becomes. Zoom out slightly further, and Brook Mine looks less like an isolated curiosity and more like the first confirmed hit from a hypothesis the Department of Energy had already spent the better part of a decade quietly testing. That coal country across the United States, from Appalachia to the Illinois Basin to the wider Powder River Basin surrounding Sheridan, is sitting on rock, ash, and even mine drainage water that was moved, treated as waste, and discarded for over a century without anyone checking it for exactly this kind of trace mineral wealth. Brook Mine is the first place where that theory turned into an operating mine rather than a research paper. Whether it becomes the first of many or remains an unusual exception depends entirely on what the drill bits find at the next old coal property somebody finally decides to test the same way Ramaco tested this one, and on whether the pilot plant now rising outside Sheridan can actually turn Wyoming clay into finished oxide as cheaply and cleanly as its backers believe it can. If you want to actually track whether this turns into the story its backers hope for, rather than taking anyone's word for it later, there are a small number of concrete checkable milestones worth watching over the next couple of years rather than vague promises. Whether the pilot processing plant actually reaches operation on or near its stated middle of 2026 target, and whether the recovery rates it reports once running match what the preliminary economic assessment assumed, will tell you more about the project's real prospects than any dollar figure attached to the resource estimate. Whether the next round of drilling across the untested two-thirds of the property confirms, expands, or narrows the current 1.7 million ton figure will tell you whether the deposit's growth pattern so far was an early-stage fluke or a genuine trend. Whether the shareholder lawsuit settles, gets dismissed, or proceeds toward trial will tell you how seriously to weigh the pace of construction concerns that Wolfpack Research raised, and whether the Department of Defense and the Department of Energy keep expanding their involvement at the site through additional research agreements, additional funding, or an eventual Defense Production Act award of the kind already given to Mountain Pass and Linus, will tell you how much confidence the government itself is placing in this specific deposit as the deadline written into the Defense Authorization Bill keeps getting closer. None of those milestones require insider access to check. They are the kind of thing that shows up in company filings, federal press releases, and court records for anyone willing to keep watching after the ribbon-cutting cameras have gone home. What changed in the end was never really about Wyoming rock chemically transforming into something new. The clay sitting under those coal seams has held the same elements in roughly the same concentrations for something like 60 million years, long before anyone called this place Wyoming, long before there was a United States to depend on it, and long before a legal deadline in a defense authorization bill made January of 2027 the date by which the Pentagon has to stop relying on a rival power for the magnets inside its own weapons. What changed was that somebody finally ran the right test on the right sample. At the moment, the rest of the world had grown desperate enough to notice what the answer meant. 130 years of drilling through that rock produced nothing but discarded core samples. 2 years of understanding what was actually inside it produced a federal cooperative research agreement, a $200 million stock offering, a state grant, a new training program at a community college, a pending lawsuit, and a pilot plant now rising out of the Wyoming ground aimed at proving, sometime around the middle of next year, whether all of that promise can actually be turned into something you could hold in your hand. That's still a real open question. But it isn't an abstract one anymore, and it isn't sitting untested in a filing cabinet somewhere waiting for somebody to eventually get around to it. Trucks are already moving material at that site. Contractors are already pouring foundations for a processing plant that didn't exist a year ago. Federal scientists are already working alongside a company that, 4 years ago, would have described itself accurately as nothing more than a small Wyoming coal operator. A magnet factory in Texas is already scaling up production, based partly on the assumption that more domestic oxide from Mountain Pass, and eventually, if things go the way Ramaco hopes, from Wyoming as well, will be there to feed it. While a separation plant halfway around the world in Malaysia races to add the same heavy elements to its own lineup. Whatever verdict history eventually reaches about how much this particular deposit changes, the process of finding out has already started. And it started the day somebody looked at a piece of clay that 130 years of miners had walked past without a second glance and decided to ask what it was actually made of. If a story like this is the kind of thing you want more of, the kind where an ordinary object turns out to be carrying a much bigger story underneath it, the best thing you can do is stick around for the next one, because there's no shortage of ground on this planet that still hasn't been asked the right question yet. Hit subscribe if you want to be there when the next one gets answered. Drop a like if this one held your attention the way it should have, and leave a comment with your honest guess. Do you think Brook Mine ends up being the deposit that actually changes where America gets its rare earths? Or one more promising discovery that never quite clears the distance between what's in the ground and what makes it into a magnet? Either way, put your reasoning in the comments. Some of the best leads for what gets covered next come directly out of that conversation.